Okay, so it's class section 1.
Always, it's a pleasure to be here. I agonized last night about what I was going to cover today because on the last day there are always choices, and so most of this talk is going to be in the continuous setting. But in the beginning, I'm going to just say a few more words about the arithmetic setting because I really think it's a beautiful sort of setting. A very interesting thing happened that involved interactions with analysis geometry and combinatorics. So first, just a quick recap. So what were these lectures about? We're talking about finite signals from Z and D to complex numbers. And the problem that we discussed is if the signal is transmitted via its Fourier transform and some of the frequencies are lost, under what conditions can we recover the signal? So we went over the classical theory, which is a result of Matolcsi and Szuchs and independently Donoho and Stark. So that if the support of the signal, size of the support of the signal times the size of the set of missing frequencies is less than n to the d over 2, the size of the ambient space over 2, then we can recover the signal exactly and uniquely. And we spend most of our time discussing the fact that if the missing set of frequencies S is in any sense generic, then we can do much better, and we looked at it from a variety of points of view. For example, we showed that if the set satisfies any non-trivial restriction estimate, then we get a better uncertainty principle and hence a better recovery condition. If the set has better than trivial additive energy properties, once again, we have a better uncertainty principle and hence better recovery condition. And one thing we didn't go over, but we could have, and this is strongly related to the other two, is that if the Fourier transform of the indicator of the set satisfies better than a trivial estimate, then once again we have a better recovery condition. But of course, if the Fourier transform of a set satisfies better than trivial decay properties, then we have better than trivial additive energy properties. So all of these things are connected, and I did my best to show you a variety of implications, though certainly not all. Then we also discuss annihilation inequalities, which are interesting in their own right, and which sort of, to me, encapsulate the uncertainty principle very nicely. They say that if the sets E and S satisfy a size condition, typically in terms of their product, that it's not too large, then the L2 norm of the function is bounded by a suitable constant times the L2 norm of the function outside of E plus the L2 norm of the Fourier transform outside of S. And we proved this under a variety of assumptions of the set S, and in all of these instances we saw that, that uncertainty principles of various types that we discussed previously can be derived from those. Then the very last topic that we discussed was what happens in the arithmetic setting. And there's just one more result in that setting that I wanted to mention before diving into the continuous results. And so this is joint work with Azita Mayele and Jonathan Pagyanathan from 2017. I'm not describing the context of how this result was proved due to time limitations, but roughly speaking, this came up in our proof of the Fugletti conjecture in ZP cross ZP. And the Fugletti conjecture says that if you have a subset of ZP cross ZP, which has an orthogonal basis of characters, then this happens if and only if the set tiles by translation. So this is sort of a long saga of the Fugletti conjecture. Fugletti conjecture was born in 1974, and it was murdered by Terry Tao in 2003. When I say murdered, I mean murdered. He produced an example that was so simply, it literally made me cry. And when I got a phone call from Mike Lacey that Terry disproved the Fugletti conjecture, I hung up on him because I thought it was an April Fool's joke. It's a true story. Anyway, the context of proving this, the following result came up, which has a direct impact on the uncertainty principle in the prime setting. Though I'm not going to describe this in detail. It will be sort of manifest. So what does the result say? It says, suppose you have a function from ZP2 to Q. P is an odd prime. Q is not a prime. Okay. suppose that the Fourier transform is 0 for some non-zero m. Then the Fourier transform on any multiple of m is also 0. Here it's important that the image is Q, because otherwise you cannot use Galois theory. Okay? And also, if f of x is an indicator function, you have something even. What? Technology worked for like 3 lectures, so this was overdue. Okay. Anyway, so if f is an indicator function of a set, then if the Fourier transform vanishes at a vector, obviously it cannot vanish at the origin because E is not empty. Then E is equidistributed on P lines orthogonal to M. So it has the same number of points, and those lines are orthogonal to M. Just for the sake of sanity, take P to be congruent to 3 mod 4 so you don't have self-orthogonal things. It still works, but then it just gives you a headache. Okay? And so in particular, this means that if the Fourier transform of a set in ZP2 has a non-trivial 0, or has a 0, period, then the size of this set is a multiple of P. And this has all sorts of wonderful consequences. For example, there is a result in analytic number theory that says that Kloosterman sums don't have any zeros, with obvious restrictions. And, you know, it takes some work to prove this, but it follows from this instantly because you can synthesize the Kloosterman sum as a part of the Fourier transform of an indicator function on a circle, and the size of the circle is P plus or minus 1, which I'm pretty sure is not a multiple of P. Okay? And so this is a mechanism. And as far as its impact on the uncertainty principle, I think that's pretty clear, right? Because you know that once you look at the support, if the support is a cone, so if you're choosing the set randomly, it is very unlikely that it contains a full line. There's a nasty calculation one can make to make it all precise, but I think that this is good enough for now. So the point is that in the case when P is prime or when other arithmetic conditions are satisfied, one can do a lot. The reason I chose not to put too much emphasis on in these lectures is because for all practical purposes, it does not make a whole lot of difference. Because, for example, I mentioned Chebotarev's theorem, which says that any k by k minor of a Fourier matrix has a non-zero determinant. And while this is not true if n is not prime, it is essentially true. So there's a beautiful result by Kendis, Romberg, and Tao, which says that with overwhelming probability, if you choose any k rows and you choose k columns randomly, then the determinant of the resulting matrix is non-zero. Okay, so let me go ahead and spend the rest of this lecture discussing the continuous setting, where I think that there are also some.
But this previous slide,
yeah,
the line, the display line, what is n?
What is who?
N. You have a formula.
Oh, n of t. Okay. So n of t is the number of points on E on the line x dot m equals t, which allows you to just recycle everything. And right, and here is the equidistribution result. You will find the proof very familiar because this is essentially how Chebotarev's theorem is proved. Although, to be honest, I never hesitate to admit ignorance. When we proved this, we did this by hand and we didn't know Chebotarev's theorem, even though it was proved in 1924. It's okay. Anyway, so if you compute the Fourier transform of an indicator function of a set, so take zeta to be the primitive root of unity, and suppose that it equals 0, then you write it out as n of 0 plus n of 1 zeta plus n of 2 zeta squared, n of p minus 1 zeta to the p minus 1. Well, so this is a polynomial satisfied by the primitive pth root of unity. But we know that the minimum polynomial of zeta is 1 plus zeta squared up to zeta to the p minus 1. And this tells us that this polynomial must be a multiple of this one, which means that n of t is constant. So E must have equal number of lines on the lines perpendicular to m. And these are the lines x dot m equals t. what makes mathematics worthwhile, is once in a while encountering things like this. Okay, all right, so let me go ahead and move into the continuous setting where I'm going to slow way down. Because I just realized that I'm talking fast as usual. All right, so the remainder of the material is going to be dedicated to the following topics. How many of them I'll have time to cover, we'll see. So one is the spectral synthesis in RD and connections with restriction theory. The word spectral synthesis in mathematics, as you know, is like the word normal. It means whatever you want it to mean. I'm going to define it. 2 is the uncertainty principle in Riemannian manifolds. And 3 is a random variant of the Shannon-Nyquist sampling on Riemannian manifolds in a new continuation of the Laplace-Beltrami operator. So you should view what you're going to see today as an attempt to recreate some of that theory in the continuous setting, though it will not, the connections will not always be obvious. I'll do my best to elucidate. Okay? All right. So here's one of my favorite results in analysis, even though it's quite simple. It's due to Agranovsky and Narayanan. Okay, so I have a student working on this, and I told the student that I never had trouble pronouncing Agranovsky, but I had trouble pronouncing Narayanan. And he said, well, it's funny, I never had trouble pronouncing Narayanan, but I always had trouble pronouncing Agranovsky. His student is from India. Anyway, so suppose that f is a locally integrable function, and the Fourier transform is supported in S, which is a k-dimensional submanifold of RD. And suppose further that f is an LP for some p less than or equal to 2d over k. Then f is identically 0. Okay? So I think it should be pretty clear why I'm calling this a version of the uncertainty principle. This time, so uncertainty principle says that, first of all, one can derive the classical uncertainty principle from this. We'll discuss this later. But also, it's the same flavor of a result. You're restricting the Fourier transform, and you're putting a limitation on the structure of the function. Okay? And there's a natural question of whether the exponent 2d over k is sharp and what it has to do with restriction theory. So up until 24 hours ago, I was going to tell you about a conjecture that links this problem with restriction theory. Instead, I'm going to tell you today why I no longer believe it. Okay? All right, so it turns out...
When you say submanifold,
oh, just a smooth k-dimensional, nothing fancy. K-dimensional with a focus on k strictly less than d, right? So we want to deal with thin, so-called thin sets of measure 0. And everything I'm going to say is going to generalize pretty easily to, say, sets of a given packing dimension. Okay? So it turns out that in the case of the sphere, the Agranovsky and Narayanan result is sharp. But in the case of some other manifolds, it is not sharp, which raises a question of why. And we'll try to address it. Okay. So I'm going to give you a proof of Agranovsky-Narayanan theorem. I'm going to prove it up to an endpoint. This is one of many results in analysis where to prove it up to an endpoint takes 3 lines. To prove an endpoint doesn't require any new ideas, but you have to write for several pages, and I just don't want to do that. Okay. And so you take chi to be a compactly supported C-infinity function, integral is 1, and we dilate it in the usual way. So chi epsilon of x is equal to epsilon to the minus d chi of x over epsilon, right? So just standard. Okay, and then we take u epsilon, which is u convolved with chi epsilon, where u is f hat. Now remember the assumption. The assumption is that the Fourier transform is supported in S, which means that u epsilon is supported in the epsilon neighborhood of S. Okay? And by the way, it occurred to me that there might be people in the audience who are not used to with these obnoxious analytic manipulations. So please, again, stop me anytime for any reason. Okay, so by Plancherel, the L2 norm of u epsilon is just bounded by this. We take a Fourier transform of the convolution, we get a product. And this is an integral of f of x squared, chi hat of epsilon x squared dx, square rooted. And this chi hat of epsilon x, for all practical purposes, simply means that we are integrating up to norm x less than or equal to 1 over epsilon. There are tails because our d is annoying this way, but it's not a big deal here. Okay? And so this is bounded by the LP norm of f times epsilon to the power of minus d over p prime. So this is just Holder's inequality. We bootstrap L2 into LP. We've seen this countless times in the previous lectures. And then we encounter this negative factor of epsilon. By assumption, this LP norm is bounded, and this is what we are going to play against. Okay, life is good? So now take psi to be a smooth cutoff function, and let's pair it with u epsilon, take a modulus and square it. So this is bounded by the L2 norm of u epsilon squared, which we just estimated, times the integral over s epsilon of psi of epsilon squared dc. Okay? So what is the point? The point is we want to pull out the size of the epsilon neighborhood of S and play it against the negative power of epsilon. Okay? And so once again, we already bounded the L2 norm of u epsilon, so we get LP norm squared, which we are assuming is finite, times epsilon to the minus 2d over p prime, times the L infinity norm of psi squared, this is a completely harmless quantity, and the volume of the epsilon neighborhood of S. Now remember, S is a k-dimensional manifold. So this is bounded by epsilon to the minus 2d over p prime times epsilon over d minus k. And this goes to 0 if p is less than 2d over k. Okay? And I suspect that every person in the room can recover the endpoint in 20 minutes or less.
Sorry, why epsilon to the d minus k?
Oh, because this is an epsilon neighborhood of a piece of a manifold, right? So you cover it by balls. Every ball has volume epsilon to the d, and there's epsilon to the minus k balls by the grace of God. Yeah. Okay, and that up to the endpoint gives us a Granovsky-Narayana. Make sense? Okay, again, the key was that less pairing step in order to expose the properties of S epsilon. Okay? And it's not too difficult to recover the endpoint. Again, the question is, to what extent is this sharp? Okay? Also, noting that the same argument works for any set of packing dimension, not necessarily an integer, especially if you're willing to give up the endpoint. And I'm really not exaggerating here because it's no longer true that the size of S epsilon is approximately epsilon to the d minus k, but if you are willing to give up logarithms, you still essentially have this. Right? Okay, so sharpness. If S is the unit sphere, then how do we see that the exponent is sharp? We write down the Fourier transform of the surface measure on the sphere. I'm certain there are factors of pi missing here. I don't think I've ever gotten them right in my life. But up to constants, this is correct. So you have a Bessel function of order d minus 2 over 2 at norm c. I think it's 2 by norm c. And then you have norm c to the power of minus d minus 2 over 2. The Bessel function decays of order minus a half at infinity. And it's just simple exercise in integration to see that this is an LP if and only if p is bigger than 2d over d minus 1. And that means that if we take a function whose Fourier transform is just identically 1 on the unit sphere, we see that this result is sharp. On the other hand, another natural example that everybody likes, the moment curve, a very high positive proportion of people in this room has suffered with the moment curve at some point or another. So you take tt squared, t to the d. Then this is a result, I believe, of, I should have looked that up, Chubarikov and Karatsuba. It is 2 by the first. Oh God, I actually remember this. Okay. And they proved that the Fourier transform is in LP if and only if P is greater than this quantity, D squared plus D plus 2 over 2. And notice that this is strictly greater than 2D over K in dimensions 3 and higher. In dimension 2, they coincide because there's no, I was about to say, there's no difference between parabola and a circle. This is a controversial subject matter. But a bane of my existence, it has been for about 20 years, is that I don't know of a single result in harmonic analysis that really distinguishes between the circle and the parabola. And I can talk for days about how annoying this is, but this is not the subject of these lectures. All right, so there are reasons to believe, at least superficial reasons, maybe a little bit more than superficial, that the exponent obtained by Agranovsky and Narayanan is not sharp, which raises a question of what does one do to get at the meat of this problem, right? So what I'm going to describe is a geometric approach to spectral synthesis, a very elementary geometric approach, okay? And I'm going to be careful with what I am proving and what I am burying under the rug. I'm not going to bury anything under the rug that is truly difficult. It's just annoying, okay? So take a set S. So S, we can always take S to be compact, and cover it by a collection of finitely overlapping rectangles. So we have a collection Rj delta from j equals 1 to n of delta. Their volumes go to 0 as delta goes to 0. Okay? And now I'm going to try to keep technicalities to a minimum, but we need to take a smooth partition of unity subordinate to these rectangles. Now, the fact that these are rectangles matter. Okay, let me stress that. So since the f hat is supported in S, and we are thickening S here, it is enough to consider on the Fourier transform side this function, f hat of c times the summation of these cutoff functions, mu j theta of c from j equals 1 to n of theta. Okay, this makes sense?
Sorry, I missed it. What is mu j delta?
Mu j delta is a smooth cutoff function that is subordinate to the rectangle. And again, let me stress, because I cannot stress this enough, the fact that these are rectangles is essential. This is not, yeah, I will describe why. Okay, so what do? The L infinity norm is approximately the L infinity norm of the convolution of the Fourier transform of that function. Okay? Okay, technically it's an inverse Fourier transform, but this does not endanger the socialism. Okay, anyway, and and this is bounded by the LP norm of F times the LP prime norm of this summation from j equals 1 to n of theta, mu j delta hat. And you should think of these as the Fourier transform of the indicators of those rectangles. It's only for annoying technical reasons that we have to use this partition of unity. Nobody likes it, even the analysts. All right, so how do we estimate the LP prime norm of this? Okay, we remember this wisdom that I think many people learned from Charles Pfefferman, who said in many talks that LP spaces don't exist. It's a myth. There's only L1, L2, L4, and L infinity. And everything else is obtained by interpolation. The thing is, this is almost not an exaggeration. Oh, no, you definitely disagree. Yeah. I am sorry. I said this in a wrong company. Okay. Absolutely. But in this context, it works. So, we are just going to compute the L2 norm, the L1 norm, and then we are going to apply restore and interpolation convexity. Okay. By the way, I heard Pfefferman say this at the same conference where he demystified Stein's analytic interpolation theorem by showing that it can be proved the same way as restorant by simply sticking complex parameters in there. It was very cute. Since then, everybody said that they always knew it, but it's not true. Okay, so the L2 norm is simply bounded or approximately, equal to the volume of this union of rectangles. Remember, they're finitely overlapping. And here, I'm not keeping track of constants. I would go bananas. Okay? So it's a summation of the volumes of Rj delta raised to the power of 1/2. So this is just Plancherel. Okay? And here, this is identically equals to. We're going to call this volume of S delta to the 1/2. Now, what I want to stress is that S delta here is not necessarily the delta neighborhood of S. Sometimes it will be, and sometimes it won't be. It depends on the choice of rectangles. Yeah, you'll see in a moment an example where this is not the case. It's actually the key, in some sense, the key to the whole thing. Because if you try to fit a round peg into a square hole or the other way around, you actually run into problems. Okay? All right, so this is what I mean by S delta. It's the union of those covering rectangles. Okay. So this is, and I will stress this in a few minutes.
Is it thickened rectangles?
No, the point is not just they're thickened, it's just that they may stick out of the delta neighborhood. And I will give you a specific example where you'll see that they have to stick out.
They can be geometrically interesting.
That's right. And on the other hand, since Rj deltas are rectangles, so pretend that here we have a Fourier transform of an indicator of a rectangle. And pretend that the Fourier transform of an indicator of a rectangle really equals the volume of the rectangle times the indicator of the dual rectangle. This is almost true if you ignore the Gaussian tails. Then what you get is the sum from j equals 1 to n of delta, the volume of Rj delta, and this is the dual rectangle. By dual rectangle, I just mean a dual of A by B rectangle is 1 over A by 1 over B rectangle. And then you get approximately the number of elements in your cover. Okay? And now things get fun. So by restoring the LP prime norm of the Fourier transform, the collection is bounded by the size volume of S delta to the 1 over P times n of delta, this is the number of rectangles, raised to the power of 1 minus 2 over P. I did the arithmetic correctly. I checked many, many times. Okay? So again, this is just by convexity. So this gives you a mechanism for studying this problem, and we're going to see a few manifestations of this. Okay? Any questions up to this point? This makes sense?
Manifestation. How about Karasuba? Manifestation?
Yes. I wouldn't have brought him up unless I was planning to bury him once more. Okay, so the idea is to find the largest P for which this quantity tends to 0 as delta goes to 0. And let's make sure that we don't lose track of things. So we bounded the L infinity norm by the LP norm times this magic quantity. So if we find P prime so that this goes to 0, so that the LP norm is finite and this quantity goes to 0, that means that the L infinity norm of F is 0, and that means that F is 0 almost.
Again, it means that the L infinity norm
Is identically 0.
So F 0.
Yes. Yeah. There's nothing tricky here. I'm not trying to over-mystify this. Yeah, that's right, if it's just 0. My apologies. No, I did make a mistake. All right. And so here is a flat example. I mean, the simplest knuckle-dragging example. Suppose that S is a compact piece of a hyperplane. Cover it with a single 1 by 1 by 1 by 1 by delta rectangle. Okay? So it follows that the size of S delta is approximately delta, and n of delta is equal to 1. Wonderful. So then we conclude that, remember, we obtained this by restoring. So this is the LP prime norm of the Fourier transform of the cover. That this is delta to the 1 over P, which goes to 0 for any P less than infinity. So what this means is that if you have a function whose Fourier transform vanishes on a hyperplane,
I don't understand. We have many rectangles. Y and delta is 1.
oh, because I can cover it by a single rectangle. I just have a piece of a plane, and its delta neighborhood can just be covered by a single rectangle. Okay. And so this tells us that p less than infinity. So this is the most trivial case, and indeed we don't need this technology. We've known this from early age. If the Fourier transform is supported in a hyperplane, and the function is in any LP class for p less than infinity, the function is identically 0. Okay? Let's look at a slightly less trivial example, in fact, much less trivial, the case of a sphere. Remember, we already saw that the exponent, the 2d over d minus 1, a Granovsky and Raynon exponent, is sharp here. So you cover S by what I've always called Pfefferman rectangles, delta to the 1/2 by delta to the 1/2 to delta. So finitely overlapping rectangles. Then here we do essentially fit inside the delta number. So the volume of S delta is approximately delta. And n of delta, the number of rectangles you need, is delta to the minus d minus 1 over 2. Okay. Again, this is all very old. So now when you interpolate, you get volume of S delta to the 1 over p times the number of rectangles to the power of 1 minus 2 over p. And this is bounded by delta to the 1 over p. And then delta to the minus d minus 1 over 2 times 1 minus 2 over p. You do the algebra, again, the trick of doing it 3 times. And you get delta to the d over p minus d minus 1 over 2. Okay? And that gives us the critical value 2d over d minus 1. I already told you that I'm just, for the sake of simplicity, I'm giving up the endpoint. A Granovsky and Raynon result gains the endpoint, but this is not her. Okay? So, right? So, this shows how this method, this simple geometric method, allows you to recover the result in the case of a sphere. Okay? And now, Chubarikov and Karatsuba. So S is tt squared t to the d. We have somebody in the room who spent countless hours dealing with this curve. Okay. And so we cover it by rectangles delta to the 1 over d times delta to the 2 over d up to delta tangent rectangles. And the way I chose the scaling is deliberately misleading. Deliberately misleading. Because it could lead you to believe that you can fit these rectangles inside the delta neighborhood of the curve, and you can't. You simply can't. They have to stick out because of torsion. And, all right, and this can be done with finite overlap. This is a calculation, and it's a moderately nasty calculation, but it's not a calculation that you can actually get wrong unless you're really trying. It's just a nasty calculation.
Does it mean that every time we're looking for like best tessellation, so best coloring, and this is sort of the best one?
Yeah, this has to be it. I mean, what else could it possibly be? Yeah, right, because we're essentially taking a tangent. And all right, so now the volume of S delta is not delta to the d minus 1, right? It's delta to the d plus 1 over 2 minus 1 over d. Because you need delta to minus 1 over d rectangles, and each of them has volume delta to the d plus 1 over 2. Why? Because you take 1 plus 2 plus 3 all the way up to d. That's d times d plus 1 over 2. You divide by d on the bottom, and you get d plus 1 over 2. I actually got that wrong the first time. Well, because, you know, when you sum integers up to d, I always forget whether you go up or down. So I just tested on the example, like d equals 3. All right, so we have this. And now we conclude that, so what do? We take the volume of S delta to the 1 over p times the number of rectangles equals raised to the power of 1 minus 2 over p. So here we have delta to the d plus 1 over 2p. Here it's delta minus 1 over dp. And here it's delta to the minus 1 over d times 1 minus 2 over p. And if you do the arithmetic, you will see that p critical is indeed d squared plus d plus 2 over 2, which is what Chubanikov and Karatsuba got. And this is a paper. This is a recent joint work with Xiaoming Guo, Ru Zhangzhang, and Pavel Zorin-Kranich. Pavel disappeared. Anybody knows what happened to him? Oh, okay. So, as I said, so if d is bigger than or equal to 2, and 1 is less than or equal to p less than d squared plus d plus 2 over 2, if f is an LP and the Fourier transform is supported on this moment curve, then f is identically 0, and by the Chubanikov-Karatsuba result, this result is best possible. And again, I've noted this before, but let me stress this again, that a Granovsky and Narayanan theorem gives us 2D, which is considerably worse in dimensions 3. Okay, so
to recap, so what was used? There was this geometry, how to cover, and before that there was restriction theorem.
Well, a Granovsky and Narayanan result uses nothing, and that's not a criticism. This is actually a praise. It simply uses the fact that the volume of the epsilon neighborhood of a K manifold is epsilon to the d minus k.
I'm not talking about the Granov, I'm talking about this one.
Oh, for this result, all that was used is that you can cover the moment curve with finite overlap by natural rectangles with side length delta to 1 over d, delta to 2 over d, etc. up to d. Yes?
But something else before that also was used, right?
No. So if we go back here, so here's the mechanism. The mechanism is we bounded the L infinity norm by the LP norm times the LP prime norm of the Fourier transform of the cover. So this is really it. It's really about this. Of course, what is harder than it looks is to come up with these covers in any given situation. Okay, and so let me go back to this, and here's something that I'm going to describe in more detail. But what is this d squared plus d plus 2 over 2? It is the integrability exponent obtained by Chubanikov and Karatsuba, but it's also, and this is of course related, the sharp Fourier extension exponent for the moment curve. Okay, so, and I will write this down precisely. And this is why when we were writing this paper, we privately conjectured, but out of abundance of caution, we didn't put this in the paper, and I'm very happy that we didn't. It seemed natural to conjecture that this is, in fact, the best extension exponent. So remember, when we were doing these uncertainty principles, then the key was the largest LP restriction exponent. So there was an LP LQ restriction theorem, and we wanted the largest P. But an extension theorem is the dual of the restriction theorem. So it makes sense that we now want the smallest Q instead of the largest P, simply by duality. And I will say this more precisely in a moment. Okay? And, all right, so once again, as a reminder, the restriction conjecture, let's say for the sphere, says that the LR norm of the restriction operator is bounded by the LP norm of the function, where P is less than 2D over D plus 1, and R is less than or equal to D minus 1 over D plus 1 times P prime. And when you write it in this form, it's the LP exponent that's important. The R is really immaterial. Okay? Now, it is convenient often to state the dual of this inequality, and we already saw that in the context of signal recovery and uncertainty principle in the discrete setting, when Bourgain's formulation, which is essentially extension, not essentially, they are extension theorems, were very, very convenient, gave us a very convenient mechanism for recovering uncertainty principles. Okay? So the dual of the restriction conjecture says that if you take a function on the sphere, multiply it by the measure on the sphere, take the Fourier transform or inverse Fourier transform, who cares? LQ norm is bounded by the CPQ LP norm here, where Q is bigger than 2D over D minus 1. The P here is really immaterial. Okay? So 2D over D minus 1 is, remember, is what we got as the critical spectral synthesis exponent. So in general, it makes sense. It seems to stand to reason that we should consider the best possible, i.e. the smallest possible, LQ exponent in the extension inequality. Okay? And as I said, in the case of the moment curve, Q has to be bigger than D squared plus D plus 2 over 2, which is exactly the exponent that we saw. Okay? And so as of this morning, I no longer believe in this conjecture. Okay? And I'll tell you why I no longer believe in this conjecture. Because up until yesterday, I never wrote the geometric method in a conceptual form. I've used it in various situations, but yesterday I finally wrote it in this conceptual form. And then what was staring me in the face and what finally penetrated my thick skull is that this covering property is really the only thing that matters. Okay? Which means that in order to disprove this conjecture, it would be enough to construct a strictly convex surface S, which has non-vanishing curvature in the sense of delta caps. So in the sense that you can cover it with the natural rectangles, but which does not satisfy the restriction conjecture. And I think that, so Zain and I were talking, and we believe that such a thing must exist. Because there's no way the restriction conjecture holds without some kind of smoothness. Okay, and one can construct a convex surface like this, which is not even C2, it's C11. And believing that the restriction conjecture extends to C11 convex surfaces with geometric curvature condition is just too much. So I was up very late trying to construct an actual example. It's going to take more than one day, but I think it's going to happen. So in other words, the Agranovsky-Narayanan problem is really about much more basic geometric properties of surfaces, whereas the restriction conjecture definitely has a smoothness component. So it's not the same problem. Okay, so in the remaining 16 minutes, I would like to discuss other manifestations of the uncertainty principle in the continuous setting, and this is on Riemannian manifolds, and this is joint work with Zita Mayeli and Ellen Wyman. In fact, it's ongoing joint work. So one thing that I also realized this morning is that this is the first time I've ever given a lecture series on a material, where all of the new results were established in the past year, and most new results were established in the last 2 months. Okay. So M is a compact Riemannian manifold without a boundary, and Ej from j equals 1 to infinity is the family of L2 normalized eigenfunctions of the square root of minus Laplacian. So I like operators of order 1. Okay, now suppose, again, we want to play the same game. A is a measurable subset, and we wish to recover the indicator from its Fourier coefficients. I'm using the term Fourier coefficients liberally. Okay? With frequencies in the set of j's, so that lambda j is in S. Okay, so those are missing. And S is a subset of lambda, the set of eigenvalues of the square root of minus Laplacian. So again, let's try the most direct, the most trivial approach. So the indicator function of A, we can write it as its Fourier series in terms of the eigenfunctions. Then we sum over the known frequencies plus the sum of the unknown frequencies. Okay, we've seen this so often. It's starting to remind me of the Blockbuster commercial from the 80s. I think younger people don't even know what Blockbuster is. It's where you could rent videos. And there was this great Blockbuster commercial where they showed a scene from Karate Kid, and they said, "You've seen this movie so many times, you should be a black belt by now. Go to Blockbuster and get another movie." Anyway, Blockbuster existed. Okay, so again, we have known frequencies and missing frequencies. Okay, so we attempt the same trick as before. We apply Cauchy-Schwarz, so we bound it by measure of a to the 1/2 times the sum of the Fourier coefficients squared, and here we run out of luck rapidly. Because anybody who has ever worked with eigenfunctions on compact Riemannian manifolds knows that they typically grow. That essentially the only case up to nonsense where this doesn't happen is on a torus. By nonsense, I mean very similar. Manifolds, etc. Okay, so if the eigenfunctions are bounded, we can run the same argument and get an exact recovery condition, right, provided that the size of A is bounded by some constant times 1 divided by the number of missing frequencies. Okay? If the manifold is homogeneous in the sense that there exists a transitive group action on this manifold, okay, a sphere is one example, then the argument also goes through. But in general manifolds, the situation is less clear. So this is very much work in progress. And at this point, I would hesitate to even formulate a conjecture. In other words, I am really not sure whether the size of manifolds is an obstacle or not. On the sphere, where you do have transitive group action, it's not an obstacle. But that doesn't mean that this is going to hold in general. So the final topic that I would like to discuss is sampling in manifolds. So sampling in manifolds. Okay, the basic question we ask is the following. So you have an MG is a compact d-dimensional Riemannian manifolds. E1, E2 through En are eigenfunctions of the Laplace-Beltrami operator on M, where the corresponding eigenvalues lambda 1 through lambda n are not necessarily the lowest n eigenvalues, just n eigenvalues. Okay? And when can we learn a function f in the span of E1 through En by observing its value on some finite set of points x1 through xn? Okay? By the way, until I heard Sasha Wolberg's talk in Atlanta, I was not learning functions, I was recovering functions. But now I'm learning functions. I think it's a cool terminology. Okay? So note that given such an f, we need to only identify its Fourier coefficients in this expansion. Okay? But look, we can simply write a vector, f of x1 through f of xn. Then we can write the Fourier matrix, which we have already seen many times in several different lecture series, times the coefficients a1 through an. And this is called this matrix capital A, applied to little a1 through an. So the recovery problem is equivalent to the matrix A having a left inverse. So in particular, this means that little m is bigger than or equal to little m. Okay? And, all right. So how do we make this happen? The Nyquist-Shannon sampling theorem, I wrote that it's ancient, but I think it's ancient means 1948. But I just don't believe that. There's really, I just don't believe that. As I said, it is implicit. If you don't believe me, take a look. There's a paper in French by Bonny from 1793. Take a look and tell me that this is not in there. Okay? If I'm misreading something, I think it's there. Okay, so It says that if M is the one-dimensional torus, and the frequencies of F are in the interval from -m to m, then one can recover F from any net of separation less than or equal to 1 over 2m. This is not difficult to prove. And this result was generalized to the setting of Riemannian manifolds in a very nice paper by Isaac Besenson in 2008. So if M and G is a d-dimensional Riemannian manifold, and F is a finite linear combination of eigenfunctions Ej with the corresponding eigenvalues bounded by capital F, then F can be recovered from approximately the size of M to the d suitably separated samples. So I just noticed that there's a crime being committed here, that is capital M refers to the manifold and also refers to the limitation. If you do this in an undergraduate class, you get skinned alive. Okay. Anyway, sorry about that. I will fix that promptly. Okay. And so here's the point. This type of a result is efficient if the spectrum of the function consists of all the possible eigenfunctions in the range, or at least a positive proportion of them. But imagine that even in a torus, that your frequencies are between -m and m, but the number of frequencies you're actually using is k, which is much, much smaller than m. Then this is no longer very efficient, and this is what I'm going to say in the next few minutes, what I'm going to talk about in the next few minutes. Does the problem make sense?
Yeah. Does it mean in the first bullet, it's just like discrete Remez inequality?
Yeah, essentially, yes. Yeah, so we have a function and a manifold. We want to learn this function, and we know that it's the eigenvalues are in a bounded range. Okay.
And what does it mean? I mean, in the first case, it's just you take net, which is a little bit close to each other, like that, and then you recover the function. But what does it mean in the second bullet? Recovered from MD suitably separated samples.
Well, on the manifold with respect to the Riemannian metric, you
don't need one net, you need many nets? So I don't quite understand.
No, you just need one net. But any net with that property.
So it's number of guys in the net. What is M to the D?
M to the D is the number of elements in the net. Because in variable 1 you need M, right? But otherwise you need M to the power of the dimension. Make sense? Okay. All right. So here, let me give you a few theorems. So let M and G be a compact connected Riemannian manifold without a boundary, and E1 through En is an orthonormal set of the Laplace-Beltrami eigenfunctions on M. And if x1 through xn are chosen independently and with uniform probability from M, then the determinant of the resulting Fourier matrix is not 0 with probability 1. Okay? Right, so this is one result. Let me elaborate on this result a little bit. And in fact, one can combine the proof of the previous theorem, which is not very difficult, with your favorite Lagrange operation theorem, say. Then if M and G is a compact connected Riemannian manifold without a boundary, again, E1 through En is an orthonormal set of Laplace-Beltrami eigenfunctions. Then if x1 through xn are chosen independently and with uniform probability from M, then there exists a positive integer k bigger than or equal to 2, such that the probability, so the determinant is less than or equal to epsilon, is in fact bounded by a constant times epsilon to the 1 over k.
So k is a function of the manifold?
Yes, k is a function of the manifold. The way these results are proved is by using the strong unique continuation property of the solutions of the Laplace's equation, because eigenfunctions satisfy the equation Laplace EI equals minus lambda. Right? They satisfy strong, so they cannot, so if they vanish to infinite, so if you have vanishing of infinite order, it's identically 0, which means that the order of vanishing is finite, You can apply Lagrange preparation theorem, identify that finite index. God only knows what it is. This is not a constructive argument, right? In fact, finding constructive means of determining this index is an interesting question, which I don't have time to address. But then you get this result.
How about, how are they called? Homogeneous harmonic polynomials.
Right.
Like an example.
Yes, in the case of a sphere, in the case of anything decent looking, this can be done explicitly. But in general, it seems to be a difficult problem. But, and you know, even the most basic things we haven't had time to work out. Like, for example, constructing a family of manifolds for which this K can be arbitrarily large. This cannot be hard, but we just didn't get around to it. This is all very fresh. So there's a number of very basic properties of this that is begging to be worked out, and this will be done.
So maybe this was answered already. Could it be that by choosing a different orthonormal set, the value of K changes, or?
Even this I don't know. So I think, okay, no. I think that by the usual compactness, silly compactness arguments, there is a K that will be the largest since the manifold is compact. But this doesn't nullify your question. But there is definitely the largest K that can arise just from basic considerations. And here is a corollary. Again, you have the same manifold, and you have E1 through En are the normal set of Fermi eigenfunctions. Once again, we choose x1 through xn independently, and this follows from the previous result very easily. Nevertheless, it's important to understand the distribution of the lowest eigenvalue for stability type results, right? So the probability that the lowest eigenvalue is less than or equal to epsilon is bounded by the constant times epsilon 1 over nk. I mean, this is trivially follows from the previous result because the determinant is the product of the eigenvalues. Okay, and as I said, the proofs of this, I didn't write out the proofs of this, but all the proofs here follow from the strong unique continuation property of the Laplace operator. That really does have to be used. So in other words, analytic machinery really is essential here. And I hope I got across the fact that there's a lot left to do here. Yes.
So what do you mean by strong continuation?
Oh, that if the solution vanishes to infinite order, then it's identically zero. At a point, then it's identically zero. And this is what's used in the proof of the first result, which is really the key. Right? The determinant is not zero, it's probability 1. And the others follow by using sort of trickery like Lagrange preparation theorem, etc. I think I'm going to stop there. Thank you very much.